cutting through 1, 2, 3, 4 members. Oh, wait, you told me I have to cut through 3 and only 3. Yeah, well, in this case, I'm going to get away with it because dt and nt are collinear. So all I have to do is do a moment at d to get NO. And I'm going to flip it, and I'm going to do a moment at N to get DC. So a couple of rules broken, and I'm okay with that. I like breaking rules. I am a rule breaker. Now, I don't go crazy with rule breaking, but I do like to break the rules every once in a while. That's just my nature. Okay? Now, I'm going to make the cut like this. And I have a choice, either look at upper half or lower half. So I'm going to make the cut here, and I'm either going to look at the upper half or I'm going to look at the lower half. Just like when I make a cut through here, I can look at left half or right half. I can make a cut and look at upper half or lower half. Which half do you think I should look at? Upper half. But now tell me why. Because I want to do what? I want to avoid A and Q. Why do I want to avoid A and Q? I got a pin reaction, that's 4 unknowns. Can I solve for those? No, I can't solve for those, so I'm going to try to avoid them at all costs. So the avoiding them means I should look at the upper half. Now, what I'm going to do first is I'm going to cut through, and back, and draw a free body diagram. Beam first. Because I really need to know what the reactions are. So here's the beam. Unknown force, Jy. Unknown force, Jx. Unknown force, Ky. And I have a single force resultant here, which is 1/2 base 10 height 500. That's going to give me a value of 2,500, which is either 1/3 of the base from the fat end or 2/3 of the base from the skinny end. In other words, this would be 1/3 of 10, which is 3.33. Or this would be 2/3 of 10, which is 6.67. Clearly, what is Jx? Yeah, some forces in the x equals 0, positive to the right, Jx equals 0. Am I shocked? Hell no. Why? Because beams are intended to carry loads along their axis. They're intended to carry loads perpendicular to their axis. Next, I'm going to do some moments about J equals 0. Counterclockwise positive, 10 times Ky minus 2,500, which is the single concentrated load from the distributed load, times 6.67 equals 0. Ky is going to come out 1667.5 pounds upward. Do a sum forces in the y equals 0 positive up. That's Jy plus Ky must in essence equal to 2,500. Take Ky, dump it in here. Jy comes out as 832.5, also upward. So the support reactions are pushing up against the beam. What are they doing against the truss? Pushing down. By Newton's third law, they have to be equal and opposite, so they'll be acting downward. So now I look at the cut and I look at the upper half. Here comes free body diagram, upper half. It'll look like this. Over here, I'm going to show JY, which is 832.5, KY, which is 1667.5. And yes, I have this, I have this, I have that. I didn't cut through any of these, so it's all good. So here I would still have my 1,000 here at an angle of, what's that angle? 60. Right? Same thing here, down, angle 60,000 pounds. And then I would have this here, like so. This would be D, this would be N, and I would have an FDC, an FDT, an FNT, and an FNO. That's my free body diagram. Now, let me ask this question. If you were a betting person, what would you bet DC and NO to be, tension or compression? Why? They're acting like columns. So I expect them to be negative because I've shown them pulling on the section. So this is going to be a negative. And I know this before I get there. But remember, I'm consistent all the time. Tension, 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 tension. If it's unknown, it's going in tension. Even if I have a good clue that it's going in compression, don't care. Okay? So now I'm going to come in and I'm going to write some moments about D equals 0, clockwise positive. Well, you take a moment about D, that wipes out, that wipes out, that wipes out. The only thing that doesn't is NO. So I have 1667.5 times 10 plus FNO times 10 plus 1,000 cosine 60 times 20 plus 1,000 sine of 60 times 2.5 minus 1,000 cosine 60 times 10 and minus 1,000 sine 60 times 2.5 all equals 0. You see only one unknown, F&O, here it comes. F&O is negative 2167.5, or F&O is 2167.5 in compression. Which I kind of knew that going in, that it would be in compression, and damn it, it is. You with me? Now I'm going to flip it. Instead of doing about D, I'm going to do it about N. Well, if you do it about N, NO goes out, NT goes out, DT goes out. Because their line of action goes through N. So here it is. Some moments about N equals 0. Counterclockwise positive. 832.5 times 10 plus 10 FDC minus 1,000 cosine 60 times 10 minus 1,000 sine 60 times 2.5 plus 1,000 cosine 60 times 2.5 plus 1,000 sine 60 times 2.5 equals 0. You solve this, you'll get f dc is equal to minus 1332.5, or FDC is 1332.5 in compression. Nothing unusual. I kind of got the feeling that that's the way it was going to be. So, not shocked. Let's put it that way. Not shocked. Yeah.
The reason you did some movements at
I
end,
could have done some forces in the water. Yeah. Any other questions? Yep.
for the second 1,000 times cosine 60, why did you multiply that by 2.5?
Where in the F and N? F and what about N?
And it's like plus 1,000 cosine 60.
I don't know. Should it be something else?
Good question.
Let's see. Is it not 2.5? Let's see, let's go back. If you're doing cosine 60, that's here, you're going to go to D. Well, that should be 20. That should be 20, and this should be 20. Sorry. Yep. Thanks for noticing that. All right. That takes care of the first half of chapter 6. The second half of chapter 6 is all about frames and machines. Here you go. Definition, frame. A frame is a rigid, load-bearing structure in which one or more members have loads or connections at places other than their end. What I want you to do is compare and contrast frames to trusses. Trusses, you can only have forces or loads applied at joints. That is not the truth here. You can apply it anywhere you want with frames. Frames or trusses have to be straight members. No, they can be curved if you want in frames. We could apply distributed loads. I have to kind of wiggle my way around distributed loads in order to get it in by putting a beam and making sure the beam support reactors were on the joints. I don't have to even worry about that with frames. So a frame is a multi-force member, whereas a truss is a two-force member. And I think I've made this statement before, but there it is again. A truss is a frame, but a frame is not a truss. In other words, trusses are a very specialized frame. Okay? If you compare and contrast the two, notice at least one member extends through more than two joints. At least one load is not located in a joint. At least one member is not straight. Everything that you know for trusses, think the opposite, and you'll be fine in frames. Oh, yeah. Okay? videos. I'm not saying anything that you can't copy down from videos. Now, as far as static determinacy, frames are statically determined if R equals 3n. Statically indeterminate if R is greater than 3n. What is R and what is n? R, number of reactions. Total number of reactions, not just the forms, but internal reactions too. N, total number of parts. So for example, I have this frame pinned here, pinned at B, pinned at C, and embedded into the ground like a fixed support at D. Notice I'm basically dismembering this into 1 piece, 2 piece, 3 pieces. Got it? And I've already started doing this with you way back when we started drawing free body diagrams. All that was to get you, I was in essence trying to get you to this point. Because I knew in frames we would be dismembering a bunch of frames to get to every solution. So if I were to dismember the frame, and you can do this because we've done it already. Notice AX, AY, I have BX, BY. On the horizontal piece, I have a connection between that piece and this vertical. That means equal and opposite for BX, BY due to Newton's third law. Over here, I got CX, CY. It would be equal and opposite on the vertical piece, DC, because of Newton's third law. And then at the bottom at D, I have a dx, dy, and a moment, because it's a fixed support. So if you look real closely, how many parts do I have? 1, 2, 3. How many reactions do I have? 1, 2, 3, 4. Counted already. 5, 6. Counted already. 7, 8, 9. So in this case, I would say R, which is 9, that's the number of reactions. There are 9 reactions here. There are 3 parts. 9 is equal to 3 times 3, which is 9 equals 9, statically determined. Meaning, I can dismember into pieces and solve for every reaction. dx, dy, cx, cy, ax, ay, dx, dy, and md. Now think. We multiply by 3. Why? Why do I multiply by 3? Huh? There are 3 equations of equilibrium. Some force x, some force y, some moments. Or moment A, moment B, moment C, if you wanted it. So the reason you're multiplying by 3 is because there are 3 equations. If you go back to trusses, 2j equals m plus r. Why the 2? Well, in the method of joints, how many equations do you play with? 2, some force x, some force y. So there's a reason for the 3 and the 2 and so forth. Okay? Here's an example, right here. How many pieces can I create out of this without causing internal? I mean, I can cut through here, but then I'd be looking at internal forces. I don't want to do that yet. How many pieces can I break it down into? 1. 1. How many reactions are there? 1, 2, 3, 4, 5. Because it's embedded into the wall, right? So I got 5 reactions. How many pieces do I have? Can I solve for this? So if you apply the equation, R is 5, N is 1, what's the equation? R equals 3 times N. Is 5 equal to 3? Okay, so what I do is I say, hey, 5 minus 3 gives me 2 degrees of indeterminacy. So this beam is indeterminate to the 2nd degree. What the hell does that mean? It means I need 2 more equations to be able to solve. I can't give you those 2 equations here. Those 2 equations will come when you go to mechanics of materials or mechanics of solids for you mechanicals. EML 3500 or EGN 3331. That's when you'll be able to solve a statically indeterminate problem for the first time. Okay? And believe me, the entire world outside is more statically indeterminate than statically determinate. So you're going to have to solve or learn to solve a statically indeterminate problem. And that's why the next class is much harder than this. So if you think, oh, this is terrible, you ain't seen nothing yet. When things start to deform, that's when you get lots and lots of problems. Lots of equations have to kick in order for you to solve a statically determined problem. So if I had another roller here, that would mean I'd have 6 minus 3 degrees of it. So I need 3 more equations beside the equilibrium ones. Okay? All right. Plan of attack. Nothing unusual. I, unlike Hibbler, do not have a procedure for I have a plan of attack because I'm more aggressive by nature, and Hibbler is way more passive. You can hear it in his voice. I just reviewed a couple of videos that he made for his new statics book, and you can hear it in his voice. He's very calm, very so class. What do you think? How many degrees of determinacy do we have here? And if you say the wrong thing, like, oh, it's 4, he goes, not so fast. Let's review. Whereas I'm not like that. And you know I'm not like that. I can't be like that. I don't know how to be that. All right, so if I tell you, find me all the reactions in a frame. Here's the plan of attack. Number 1, can I find this 4 reactions? If I can, by all means, go ahead and do it. Which means draw a free body diagram, the whole thing, and do a chapter 5 problem. Get the support reactions. If you can't, skip step 1, go to step 2. Well, what the hell step 2 say? Hey, take this frame and start dismembering it into pieces, just like I did for that one we just did. And you've been doing that since we drew free body diagrams. If you go back to free body diagrams, way back when, remember this? If you draw a free body of the whole thing, I'll have 1, 2, 3, 4 unknowns. But if I separate into an AB and a DC, which is right here, then I'll have 6 equations, 6 unknowns. We have done this for this one. Notice I broke it up into this piece and that piece, right? 6 equations, 6 unknowns. I broke this one up into 2 pieces. And then I realized later, when we defined what a 2-force member is, hey, that's a 2-force member. If I can do that, then I can save myself lots of grief. So we have been doing this dismembering and applying Newton's third law for pin reactions that are attached to like a member AB and a member BC. That joint B is going to be equal and opposite when I separate the 2 pieces out. And then, what do? You apply the equations of equilibrium in the order dictated by the information given. Can I find everything? Usually no. Usually no. Which means I may have to go back and forth between free body diagrams in order to get everything. Sometimes you'll get an equation, By equals Ey. Okay, but I don't have a value. Then you go to the other free body diagram, you get a value for B, you can bring it back and say, since By equals Ey has to be 100 or whatever By is. Got it? So this is what you're going to have to do for frames. And of course, if you can recognize two force members, like I told you before, you can cut your workload in half. How? Well, I showed you this already. Like I said, I've been setting you up for this moment for a while. If you go back, let's go back, right here. I did this problem not recognizing two force members. I had to draw two free body diagrams. I had 1, 2, 3, 4, 5, 6. 6 equations. Notice over here, I ended up getting a relationship. Bx equals 1.33 by. I didn't get anything but a relationship. I got a relationship. So now I do this free body diagram and I get an equation with Bx and By. I take this, bring it over here, solve. I can solve for Bx and By. Bring it back here. I can then solve for Ey and Ex. That's the working back and forth between members. That's not recognizing two force members. But then I did it again with you, saying, oh, wait, that Be is a two force member. If that's the case, then I don't need two free body, I just need one, and I'll just make this an FBE. And notice I went from two free body diagrams to one. I went from 6 equations down to 1, 2, 3. Got the exact same answers. So if you can recognize two force members, you will cut your workload in half. Okay? All right. So let's take a look at the first problem with frames. First problem. I have what's known as an A-frame. Okay. It says, pin-connected frame, find me the forces acting at all joints. So I have a pin at A, pin at B, pin at C, pin at E, a roller at H. Okay? So, step 1 says, hey, if possible, sometimes it's possible, sometimes it ain't. If possible, find me the support reactions. Do you have your testing manual with you? So, if you look at the testing manual, here's a problem. It's a frame. After you reduce this down to a single force, reduce this down to a single force, you look and say, all right, step 1, can I find the support reactions? Can I find C and D? Well, that's a pin, that's 2 unknowns. That's a pin, that's 2 unknowns. There's 4 unknowns. Can I find all of them? No. Skip step 1. Notice, I did not bother finding pin C and D. I went straight to dismembering. And then I realized, oh, wait a second. AF and BE are two force members. So what did I do in the free body diagram? I drew them in as force instead of BX, BY, EX, EYs, and I just drew it as a force. FBE and FAF. Now, do I know these are pulling? I have no idea. Nor do I know that CX, CY is to the left and upwards. Again, these are all guesses. If I get a positive answer, I guess correctly. So in this one, I did not solve for the support reactions because I can't get them all. I said, to hell with that step. Let's move on. Okay? This one over here that we're doing right now, I can solve for the support reactions. Because I can cut through here, cut through there, and back. Which means I can get, oh, before I do, I want to mention machines. This is frames and machines. This is already in your pro copy book at page 128. Machine is defined as a partially constrained frame. A partially constrained frame. You know what it means to be partially constrained. Just like you should know what it means to be improperly constrained. Right? A partially constrained frame designed to transmit and modify forces. You with me? So for this definition, a pair of pliers is a machine. Anything that will give me a mechanical advantage is what we call a machine. It doesn't have to be gas powered or electric driven. Okay? Now there are 5 uses of machines. What are the 5 uses? There they are right there. Transfer energy, multiply force, multiply speed, change the direction of a force. 5 uses. Here's the type of machines. There are 6 of them. And technically, this one, this one, this one, this one, and this one are all the same. They just have a different form. They're all levers. These are all levers. So a screw, a gear, a pulley, these are all levers. They take on different forms and shapes, but they're in essence a lever. Okay? So let's discuss the lever, because that's pretty much what you have there. Lever has 3, by the way, this is not in the textbook. A lever has 3 elements to it. Notice it's got a fulcrum, that's the pivot point. It's got a weight, and there's an effort. And based on how you arrange these 3 elements, classifies the lever as a class 1, class 2, and class 3. Class 1 lever, the fulcrum's in the middle. And it doesn't matter if the effort's on the right or left, it's just fulcrum's in the middle, and the effort and weight are on either side. Example of that would be a seesaw, oars of a boat, etc. These are all class 1 levers. Class 2 levers, you take the fulcrum and you shift it over to the left end. And then you make a weight in the middle. That's a wheelbarrow. Basically, here's the wheel, the weight is the rocks, and this is the person pulling up, is the force of hands. Right? I like crabs. So you get a nutcracker that looks like this. You squeeze here. You put the crab in the middle and you crush it so you can get to the good stuff. It's a lever. What type of lever? Notice the fulcrum right there. There's the pivot. There's the, and here's the effort. So it's really a class 2 lever. A door is a lever. It's hinged on one end. That's the fulcrum. There's a weight in the middle, and then you push on that side. What is it? Class 2 lever. Somebody got a Coke can? Or some sort of can? I want that. Every single one of you uses a can, and you open it. If you look real closely at the top, how you open the son of a bitch? Oh, it doesn't even have a lever there. You crush it. Nobody else has a can? Okay, well, if you look at your cans next time, statics is all over everything in your life, and you don't even know it. So in here, you have that. Right? is your fulcrum. Then you have this piece right here, then you have that piece right there, and you pull up, that goes down and opens the can. Right? Fulcrum, here's the effort, there's the weight. It's a class 1 lever. And you didn't even know it. You want this back? It's empty. Send it back to her. You know it. Anyway. And then the third is a class 3 lever. The class 3 lever, human arms, a crane. So look at your arms. You put something here. Your tendons, muscles are your effort. There's my pivot. Okay? Or even this could be your pivot. Here's the effort. Here's the weight. My muscles here are the effort, and there's your pivot when you do this. It's a class 3 lever. Inclined plane. Basically, you'll overcome a large resistance with a relatively small force by acting through a longer distance. That's the essence of an inclined plane. Okay? All right. Let's go back to this problem. What do I got? Well, I'm going to draw a 3-body diagram, the whole damn thing. 3-body diagram, entire frame. That looks like this. I've got HY from the roller. I've got AY, AX from that pin. I also have this that goes here. Boom, boom, and 2,000 down. I did not cut through pin B, didn't cut through pin C, didn't cut through pin E. Here's pin G to attach the pulley to the horizontal bar BEG. Okay. Some forces in the X equals 0, positive to the right, and AX equals 0. Great. Some moments at A equals 0, counterclockwise positive. HY times 10 minus 2,000 times, be careful with this distance, from here to there is 4 plus 6 is 10 plus 6, 16 plus that distance. Well, that distance is the radius of the pulley. So that's technically 19 equals 0. I get a lot of students because they don't read the diagram in detail. So HY comes out. HY is 3,800 pounds upwards. Yep. I can do a sum force and line. I'm not going to. I'm going to do a sum moments about H equals 0. Why would I do this? I probably wouldn't. I just write sum forces and hope. Why? But can I? The answer is sure. You can do a moment. You got 3 equations. How you choose to use them is up to you. You want to write 3 moments? Go ahead. You want to write 2 moments and 1 force? Go ahead. You want to write 2 forces, 1 moment? Go ahead. So I chose to do a moment just to be different. Okay, I probably normally would not do it because moments take a lot longer to deal with because I have to have distance and force and the positive and negative for it. 10 AY plus 2,000 times 9 equals 0, or AY is equal to minus 1,800, or AY is 1,800 pounds downward. Now that I have that, I move on to step 2. Step 2 says, hey, if you want to find the reactions at B and C and E and so forth, you're going to have to dismember this into pieces. So the first set of pieces is I'm literally going to unscrew this pin here, pull it out, separate that pulley. So this is going to be free body diagram, pulley. This is the easy one. I have 2,000 here. It's the same cable that runs all the way to D. That's gotta be 2,000 that way. So you can see, what's GY equal to? What's GX equal to? I'm going to write the equations just so your notes are complete. Some force in the x positive to the right, that's GX minus 2,000 equals 0, or GX equals 2,000. Some forces in the y is equal to 0 positive up. That says GY minus 2,000 equals 0, or GY equals 2,000. And they're in the right direction in the pulley as drawn. Next, I'm literally going to pull out the pin B, pull out the pin E, pull out the pin G, separate that piece out. So now I'm going to draw a free body diagram, BEG. That free body diagram is going to look like this. I have a B, Y, a BX. I have to have an EY and an EX. I have to have GX and GY, but these have to be 2,000 this way and 2,000 that way. This is GY, that's GX. Did I draw them equal and opposite to what I had in the pulley diagram? Yes, Newton's third law requires it. And this is where I'm going to get you on the next test. You're going to forget to draw them equal and opposite. Okay? So now, best thing you can do for yourself is when you write equations, do what? What equation should I write right away? Yeah! I'm going to do a sum moments about B equals 0. And I'm going to take counterclockwise positive. Moments about B wipes out that, wipes out this, and wipes out that. What's left? EY and GY. Perfect. That's going to be EY times 6 minus 2,000 times 12 equals 0. EY is equal to 4,000 pounds. I got the right answer, so it is upward on this free body diagram. Some forces in the Y equals 0 positive up. No, I didn't do a Y. I did a sum moments about E. I just flipped it. Counterclockwise positive. I said 6 times BY minus 2,000 times 6 equals 0. BY is equal to 2,000. And that is positive downward because I got a positive answer and it's downward in the free body diagram. Next, I'm going to do a sum forces in the X equals 0 positive to the right. BX plus EX is equal to 2,000. Notice, I did not get an answer. I should get an answer. How many unknowns are in that free body diagram? 4. BX, BY, EX, EY. There's no freaking way I'm going to get all the answers. And this is why it says you may have to work back and forth between free body diagrams in order to get all the answers. So next, I'm going to draw a free body diagram. Free body diagram of C, D, E, H. So this is this vertical member. I'm going to have a CX from that pin. I'm going to have a CY from that pin. I'm going to have 2,000. This is at D. Then I'm going to have equal and opposite, I'm going to have EX, EY, and I know EY is 4,000. Now, my suggestion to you is go get you some colored pencils. Okay? Get you some colored pencils. And when you get a value, like I got a value of 2,000 here at GX and 2,000 at GY. Notice I color coded it in green. To me, when I color code something other than red or black, that's saying I got this value not from this free body, but from someplace else. Okay? So I like the color coding, and if you want to do that, I'm fine with that. Notice here, this value did not come from this free body diagram. It came from this, which came from a different free body diagram. And then I have HY, which I know is 3,800. If I want an answer right away, what should I do? Come home. Where would you like to come home? C would be ideal. That would give me EX. So I'm going to come in and I'm going to say some moments at C equals 0, clockwise positive, EX times 9 minus 2,000 times 6 equals 0, or EX is equal to 1333.33. And over here, it's to the left is positive, so I picked the right directions. So now I take this guy, go back over here, that's the working back and forth, dump it in, and BX will come out. 666.67. Go back to this other free body. Oh, by the way, if I got a negative here, I'm carrying a negative in here, which means when I find BX, it's really going to be 3,333.33 instead of 666. Some forces in the X equals 0, positive that way. That's CX, not EX. CX plus EX minus 2,000 equals 0. Take this EX, dump it in here. CX comes out 666.67. Some forces in the Y equals 0, positive up. That's going to say 3,800 from HY minus 4,000 from EY plus CY equals 0, or CY is equal to 200 pounds. And it is upward. This is to the left. I'm done. You asked me to find all the reactions. Well, BX, BY is known. CX, CY is known. EX, EY is known. AX, AY is known. And the horizontal and the vertical reaction at H is known. I found everything. Now, hold on. We never ever drew this free body diagram, did we? The reason for that is you found anything you needed because you drew a free body diagram of the whole thing. If I drew that free body diagram, just saying, if I did, here's that free body diagram, right here. I have AY 1,800. I have AX 0. I have B. B is BX this way, which I know what BX is, 666.67. BY is that way. BY was 2,000. CY, that's going to be downward by Newton's third law of 200. and CX has to go that way, and that is 666.67. Stop, take a minute and look. Do I freaking balance?
Yeah.
Well, let's see. I got downward 1,800, downward 2, that's 2,000 down, I have a 2,000 up. Are the Y's balanced? Yes. Do I have 666 this way and 666 that way? Yeah. I don't need a solution manual. I don't need Chegg. I don't need ChatGPT. Fuck them all. I am the solution. And that's the way you should be thinking. I am the damn solution manual. That's what we're trying to teach you, is to be the solution manual. Because you know what, outside the real world, you have to be the solution manual. And yes, you can say, well, I'll just put it in ChatGPT. Great, except ChatGPT doesn't always give you right answers. You have to be smart enough to say, did I give you the right answer? Let me check it. Because I'm telling you, I put shit into ChatGPT, and it came back with answers. I'm like, no, that ain't the right answer. The hell are you doing, Chat? What?
Can you split the paper down a little bit?
I call it ABC, yeah. Whatever. No, you don't have to, but you have everything. I didn't need this. I didn't need this at all. I just did it to show you, you can check yourself. You don't get any points for giving me that. No. What's that? Yeah, you're fine. What?
You have to draw the arrows, like on a test, you have to draw the arrows.
Listen, at this stage, if you fucking give me 666, I'm going to say, check! We're good. I'm done. Thank God I got the 666. Holy shit. What? As long as you don't use red. I don't care. Don't use red. All right, next problem. Old test question, just so you're aware. The first thing I'm going to do is I'm going to get rid of this. If this is 300, what's this and what's this? Huh? 150, 150. Oh, by the way, there's a pin at B that I didn't draw. And an H. What's these guys? 75, 75. Let me ask this question. So now I can get rid of all that and I can say, coming into joint B is 150, coming over here is 75, coming over here, so I can get rid of all that shit. Let me ask this question. Step 1 says, if possible, find the support reaction. Is it possible to find the support reactions here? Yes! I've got CX, CY, and I got a cable tension. Those are the external support reactions. Right? But I'm going to skip step 1. I'm going to say screw it. I'm going to do it my way. I'm going to go straight to step 2. Start dismembering. Here you go. Free body diagram. BDG. That's this horizontal length. I'm going to draw 900 right here. Remember, what is this? 1/2 base times height. Height is 300. Base is 6. You're going to get 900. Acting 2/3 from here, or 1/3 from, 1/3 from the skinny end, or 2/3 from the fat end. So I'm going to put in here 1/3 from the fat end, 2/3 from the skinny end. I'm going to put in dy, I'm going to put in dx, and I'm going to put in this distance of 4. Then I'm going to put in a by and a bx. I'm going to start writing equations. Some moments at B equals 0. Clockwise positive. 900 times 8 minus dx times 4 equals 0. Dx is going to come out. 1800 positive, so it is going to the left. Some forces in the x, positive to the right. That's going to say bx minus 1800 plus 900 equals 0, or bx equals 900. Some forces in the y equals 0, positive up. That's going to say by minus dy equals 0, by equals dy. I'm not shocked because I have 4 unknowns and only 3 equations of equilibrium. Therefore, you're not going to solve for everything. Don't panic, don't cry, don't call me names. You'll get there. However, you might have to work back and forth between free body diagrams. Next, I'm going to dismember this into here, here, and there. So, free body diagram, AD. That's going to look like this. I'm going to have an AY. I'm going to have an AX. I'm going to have a equal and opposite to this, dx, dy, and I'm going to have this force, 600 here. Well, I already know dx. Bring it in. I'm bringing it into a different color, telling me, hey, I did not get this dx from this free body diagram. So, come in and do a moment equation at A. If I do a moment equation at A, I'm going to get dy. Some moments at A equals 0, clockwise positive. What do I got? dx times 4 minus 4 times dy plus 600 times 7 equals 0. We know dx is 1800. There's only one unknown, dy. dy comes out. 2850 is positive, so I guess right, it is upwards. Some forces in the x equals 0, positive to the right. Says dx minus ax plus 600 equals 0. Well, we know what dx is. It's 1800. So ax is going to come out 2400. And it is to the left. And then last but not least, dy minus ay equals 0, or ay equals dy, but what was dy? 2850. So I just found everything here. So this looks like I have dy, which is 2850, ay, which is 2850, ax 2400. Does it balance? Well, 2400 to the left, 18 and 6 to the right. That's balancing. Downward 2850, upward check. It works. Free body diagram, last but not least, of A, B, C. That's this horizontal member. I will have cable tension T. I will have a CX. Nope, took CX to the right. And a CY. In here, I'm going to put in my AX, 2400, my AY, upwards, 2850. I'm going to put in my bx this way, which is 900. It's got to be equal and opposite to this up here. I have a by headed downward, and by was 2850 because of equation 1. Then I'm going to have a cable tension, downward 150, 1 foot away 75, another foot away 75. Boom. Luckily, I can do a quick sum forces in the x equals 0, positive to the right. That's going to say 2400 from AX minus a 900 here plus a CX equals 0. CX comes out. Minus 1500. What's the minus sign tell me? You goofed. It's not going to the right, it's going to the left. Then I'm going to do a sum moments about A equals 0. That'll give me CY. Minus BY, which I know, times 4. Minus 150 times 4. Minus 75 times 5. Minus 75 times 6. Plus CY times 10 equals 0. We know BY, 2850. So CY is going to come out. 1282.5. And then a simple sum forces in the y equals 0 positive up. 2850, which is AY, minus 2850, which is BY, plus CY minus 150 minus 75 equals 0. CY is equal to not CY. T. Shit. And then I have CY here of 1282.5. So T will come out. T will be 982.5. All right, listen up. Tomorrow at the help session, I'm going to finish the pro copy book. I'm not going to teach you a help session. When we get back from spring break on Monday and Tuesday, I'm going to go through the help session problems. So that day will not be a lecture for new material. It's going to be covering the same material, but help session problems. And remember, the quiz tomorrow is distributed load and finally support reactions. You have several examples in the testing manual. Adios.